So we have Concrete is Guided Galaxy Week 9. And this one, I'm going to cover one-way slabs, which I think Taewon will cover, but very briefly. The reason I'm going to spend an entire week on it is just going to reconsolidate a bunch of various other topics, right? But just in terms of like what the topics are listed as, like in the middle, right? Topic 8 is detailing. So I think he did actually talk about this in the lectures, but it's not really in the course. At least he goes into a lot of detail about detailing. But like the other stuff that's going to be in the course are like spacing checks and stuff to make sure that your tensile rio is like far enough away apart, and cover checks and stuff like that, right? The detailing checks are like, they're really detailed basically. It's like about hooks and cogs and like the fitments and stuff like that. But we're going to focus on one-way slab, and there's only really one question that goes into a lot of detail about one-way slabs, and it's in workshop 10, and it's question 2, right? Grab my drink bottle. And then in week 10, we're going to cover columns, right? I've just put it here, but we're not going to do it this workshop, right? Yeah. I'll explain more about columns next week, basically. But one-way slabs, right? They're basically just beams, but a little bit different. And we're gonna design a one-way slab basically from start to finish. So it's gonna be like a composite topic, I guess you can call it. It's gonna have stuff from like the last 3 or 4 weeks. And it's gonna cover most of what you need to know in the finals, right? Maybe just I'll quickly outline some differences between them. So when you're doing beam design, right? First you do Flexural, then you do shear, and then a serviceability, right? For slab design, and shear, you're gonna do the concrete strength. I might write it like this. The concrete strength and the fitment strength, right? But with slabs, we do Flexural, we do shear, but I'll explain why later when we see the formula. But you basically don't need to put fitments, these ones. You don't need to put the ligatures or fitments in slabs. Like you never see them in the slab cross section. And that's because the concrete can actually take on the transverse shear, like completely fine. And then for serviceability, sorry, one other thing I should say is that for slabs, your Flexural, you have like tensile steel, it's called primary direction, and secondary direction. Tensile steel, right? For beams, you usually have tensile steel and compressive steel, right? Do you remember like the one on the top and the one on the bottom? But they're both running in the same direction, right? So for beams, that's your compressive steel. That would be like your tensile steel on the bottom, right? But for slabs, the steel will look like this in the primary direction and this way for the secondary direction. So it's like 2D, you know what I mean? But they're both tensile steel. Yeah. And then serviceability is quite important for slabs, because I think I talked about it last year, but usually think of like slabs deflecting, like this roof. You can imagine like a big sag in the middle, right? Yeah, so like I think in general I want to say slabs will experience more deflections than beams just because of how they're supported. Yeah, any questions? Okay, cool. So this is kind of like, we're just going back to something that I covered last time, but it's just the simplified formulas. So these are the bending moments for your continuous beams that is outlined in AS3600. Yeah, so you wouldn't really use these formulas for a simply supported beam cantilever, but for a continuous beam, you should use these, right? And I think Justin or something last week asked me, can we use these formulas even when here in the formula, our length, hello. Oh, Karan, one time. Yeah, like I think Justin asked me like, oh, can we use these formulas even if the spans of our continuous beam are different lengths? For example, like this, then like this, right? The answer is yes, you can. So the Ln that you're going to be referring to is going to be different depending on which part of the beam you're analyzing, right?
Is it dependent, like, are you referring to the continuous end versus the extents or something like that?
Sorry, wait.
This is the long, what's it called? The long deflection versus the short deflection.
Or short term, long term. Yeah. Yes. Right now I'm talking about just the bending moments of a continuous beams. Yeah. So these formulas are just simplifying the M star basically at various points along this continuous beam. Yeah. Here's one which I haven't shown before, but it's very similar, right? It's the shear force, right? So for continuous beams, they look like this, right? And then this value actually turns out to be the highest value, assuming all the LNs are the same, right? At the exterior face of the first internal support. Sorry, first. Yes, first. But yeah, this shear force formula doesn't change depending on whether you have two spans or more than two spans. This one is anytime you have a continuous beam, and the continuous beam can't have one span because then it would be simply supported, right? Make sense? Cool. Right. So the name one-way slab comes from the amount of whether the loads transfer in one dimension or two dimensions, right? When you're looking at it top down, right? So we're only dealing with one-way slabs in this course, right? But I'll just show you some examples of one-way slabs and two-way slabs just for the lols, right? But it's usually based on two things. One is the aspect ratio, right? So if something is like a square, 1 by 1, it can transfer in two directions, right? Because the forces the gravity loads or whatever, they want to follow the path of least resistance, right? And gravity loads go from top down. So from like the slab to the beam to the column to the footing, and dispersed into the ground, right? But if we're just focusing on the slab, and yeah, it just wants to transfer to the beams, which are on the edges of the slab, right? Yeah. And then here's when you have an aspect ratio of less than 2, right? So let's just say that's like, I don't know, your phone screen. No, that's greater than 2. Anyway, so like, basically, if this is like 2 blocks in Minecraft, and this is like 3 blocks in Minecraft, this is an aspect ratio less than 2, right? But if this is like 2 blocks in Minecraft, and this one's like 5 blocks in Minecraft, that's an aspect ratio greater than 2. You know what I mean? Yeah, bro.
The ratio between R1 and 2 should equal 2, is that correct?
No, because that should equal 1.
Okay.
But it's less than 2. 2 is the threshold number. But the beams themselves can limit the directions of the path loads. Because if they don't have beams, for example, here on the bottom edge of the square and the top edge of the square, the loads only have one direction to transfer, which is laterally, right? Oh, laterally is not a great word. Horizontally, when we're looking at it in this perspective, right? Yep. Okay, let's just go through some random examples. You tell me if the 1 or 2-way slabs. So this first one. Very good. This second one. You sure? So the beams are there, but think about the aspect ratio. Because the loads, basically this aspect ratio is like 2 blocks and this is like 6 blocks. right? Let's think about it like Minecraft blocks.
Yeah.
It's gonna end up transferring like this. Because the path of least resistance is in that one direction.
Okay.
So this is a one-way slab. What about this one?
Two-way. That's
Yep. What about this one? Very good. This one?
That's
Oh,
one way anyway.
one way, yeah.
Very good.
So the next one's gonna be two-way.
Very good. Get it?
Oh, sorry, how is this set?
The aspect ratio, here are the beams,
It's 1-to-1.
and then it goes like that. Yep. So where I've done the dashed lines are the beams basically. So all of these are separate instances of slabs that you can design. I think there's a word for it. It's like, it's not panels. Bays. They're called bays. Yeah. So these are different bays. Yeah.
As in the sides?
The size of the bays are the same size in this case, but there are 3 different bays in this two-way slab system. The bays are the red rectangles that I've drawn.
Oh,
Yeah. Anyway, yeah. Alright, all good? Okay. So, basically to design a one-way slab, we're essentially designing a really thin but fat beam. And we take something called a slab strip, which is a 1 meter width, right? And we design everything per meter run, if you've heard that word from wherever. I think in fluids they might have said that before, per meter run, or per meter into the page for like fluid design, that kind of, yeah. Or in soils, if you guys have done soils, they do per meter run design. Okay, knows what's up. Okay, yeah, but you get it, right? And then I was saying before, we have primary direction of reinforcement and secondary direction of reinforcement, right? So since we're designing one-way slabs, right? Sorry. Which direction do you think is the primary direction in this specific instance? Is it this way, or is it that way?
This way.
So here's option 1, here's option 2.
Wait.
Are you sure?
No, it'll be this way because the beams are.
So option 1.
Yeah.
So think about where the forces are transferring, right? The forces are transferring this way
Yeah.
and this way, right? And it's gonna, and then like these are supports and stuff as well, right?
Yeah.
And then so essentially here's your beam, and here's how it's gonna deflect, right?
Yeah.
And how have we designed beams? You know, let's just draw it like this. We've designed beams in this course like this, right? And for flexural design, we have our tensile rear running axially like that along the beam.
Uh-huh.
So our primary reinforcement is going to go in that same way, right?
Yeah.
So that's our primary direction. Does that make sense?
Uh-huh.
Vina, are you okay?
Yeah.
So,
The primary direction is going to be
I was just very concentrating, but yeah, I get it.
your first.
So it's the reinforcement only for the top, like such.
so in slab design, sorry, I think you missed the first minute or so. We're just doing tensile design. We only need to put in tensile rear. Well, I don't want to say only. In this course, we focus on the tensile rear for slab design. So this isn't for compressive rear. So where the bending moments are, the bending moment diagram might look something like this, right? We put the tensile rear around here for this slab. And the compressive rear is where there's your hogging moments. So that will sit kind of on the top half of the slab where there's like a support. That's kind of where the steel will sit. But it's all tensile rear, you know what I mean? We don't have compressive bars. I don't want to say that because I feel like in actual slab design we do have compressive bars, but it's not the primary steel that's taking on those forces, you know what I mean? So we don't really focus on that in this course. Anyway, so we were talking about this direction being the axial direction, right? And so that's our direction of our primary tensile rear. Okay, so why do you reckon we have rear facing the other way for a slab?
For this one in particular.
For any slab, you actually want some secondary rear.
And just so it doesn't break one way. This will be-
Yeah, that's right. So if there are forces going the other way, right? So if the entire thing sags like, I'm drawing a 3D shape here, sags like that,
Yeah.
it might split apart, right? If we don't have Rio, right? So these are the cracks forming. It's gonna split so that the rear, like in between the Rio, you know what I mean? So actually the secondary Rio, which is what we call the tensile rear in the secondary direction, is there so that the cracks don't form. It's actually for crack control.
Okay.
Make sense? But it's secondary rear. It's not as important as the primary rear taking on like the forces and stuff.
So are they like lighter?
Sorry?
Are they like the same type or like lighter because there will be a lot of weight?
Wait, I can't hear you. Sorry.
Are the secondary ones like lighter or are they the same kind?
Generally, you have less area of secondary rear than primary rear. They can be like if you use N12s for your primary direction, you can use N10s for your secondary direction or something. They can also be both N12s or something, for example. It depends, but generally there's less area. Okay, makes sense? Let's continue. Okay, so the general steps are like this. We find where the critical shear force and moments are, and that's the section we design for. We kind of design for that worst case scenario. Then we start off with flexural design, right, which will govern how big our section, actually in the question that's provided, they just tell you what slab depth you should start with. So you don't need to guess the slab depth. The width for a slab is always 1 meter because you're designing per meter. But in the question I'm going to show you, we're going to start with flexural design because we want to find the area of reinforcing steel that we need in the primary direction and then the secondary direction, right? There's some details here. These will make more sense when I go through the question, but I really want to go through the question today because it's going to take a while. It's going to be a bit, I'm basically going to slowly go through one question so that everyone understands like all the steps behind flexural design, shear design, and serviceability design, right? Transverse shear design. So basically, yeah, we'll be good. Okay, basically, this is transverse shear, right? So this is like paper towel. That's transverse shear, right? There's another concept that's not covered in this course, but it applies a lot to slabs. If I stab this pencil through, right, or whatever, that's called punching shear. It happens a lot between columns and slabs. Like, it's like a hole punch. Or like, if my fist punched through this towel. What happens is the column literally penetrates the slab, and then the whole slab falls through. As if the column was like the pencil. So there's actually two types of shear actions that happen on slabs. But we're designing specifically for the transverse shear, which is the ripping. Yeah.
So assuming that the slab is like failing.
Sorry.
Is that when that happens? That's when the slab is failing.
Oh yeah. So basically, like in structural design in general, we want to check for all the possible modes of failure, right? And in this course, we don't cover punching shear. We're just going to cover transverse shear. But usually transverse shear doesn't really govern for slabs. And you'll see why. It's because the concrete, when you have a width of 1,000 mil, it actually has a lot of shear strength, transverse shear strength. Yeah. You'll see how it plugs into the formula and why it does make a difference for beams, right? They also use the simplified method usually in slab design because again, transverse shear is not like as critical to slab design. And then serviceability design, we're going to do it for an end span in the question. And then we're also going to deal with something which I didn't really cover last time, which is the attachment of brittle partitions. So this is an extra step on top of what I discussed last week for like, yeah, anyway. Any questions so far? Yeah. So here's the question that we're going to analyze today. All right, so I'll read it first. Design the end span of a one-way slab continuous over 4 spans. The preliminary design specified that the thickness of the slab should be kept to 190 mil. The floor is to support a live load of 2 kPa and a superimposed dead load of 1 kPa due to deflection sensitive partitions, right? The slab is supported by 150 mil walls, right, which are essentially the columns, with a clear distance of 5,000 mil, which is this net length, right, net span, shown in the figure. To satisfy durability requirements in fire, we take the concrete strength to be that, and clear cover to reinforcement to be 25 mil. Limit the deflection after the attachment of brittle partitions. So this is like a deflection limit that they've specified, but there's just like an extra step involved when it says like brittle partitions. It probably won't come up in your finals. This is the only question I've seen with this little tidbit of information, right? Assume minor crack control is required. So the crack control bit of information is to do with the design of the secondary reinforcement. So depending on how much crack control you need more secondary reinforcement to make sure those cracks don't form. So there's like a minor amount, a moderate amount, and I forgot what the high one is called.
Substantial.
It's some shit like that, right? High degree, I think it's called. I don't know. Anyway. So the density is specified. That's actually not the density, that's the unit weight. Actually, that's a unit weight. And then they specify the steel yield strength and the short and long-term load factors for serviceability. They specify the shrinkage strain amount, and EC is the elastic modulus of concrete, ES is the elastic modulus of the steel, right? So we're focusing on this end span, right? And this beam continues. It says it's a 4-span beam, so it looks, slab, right? Looks like that, right? But we don't really care. We're just designing the end span part, right? Okay, so I'm gonna go pretty slowly for this question, but I want you guys to help me design this. So where would you start? Like, what's the first step? Yes. We want to get to M star at some point, but wait, sorry, what did you say, Josh?
No, basically
Okay. So how do we get to M star? Yep, live loads, dead loads. Let's call that Q and G, right?
we use the load combos.
Yep. So load combos, 1.35 G, 1.2 Q, 1.5, oh sorry, fuck. 1.2 G, 1.5 Q, right? All right, so can someone tell me what G and Q are? Well, here's the thing, right? G and Q aren't obvious. That's the first thing. So that's where we should start, right? We should calculate G and Q. So I call those the unfactored loads. We haven't factored them yet because the load combos are the factors, right? So here's the section, right? I might do Q first. The Q is a live load, right? All right, someone tell me what the live load is based on the question. Sir? Okay, good. So 2 kPa. What units is kPa?
Oh, kilonewtons per meter.
Yep. So how do we turn that into what we want, which is usually kilonewtons per meter for a distributed load? So currently we have per meter squared. Yeah, that's actually right. But why would we times it by a meter in this case in particular?
Or is it the width of the?
We multiply it by the slab width, which is always 1 meter, right? So KPA is essentially times 1 meter for slabs, right? So this can be different for a beam because a beam can be like 600 mil wide, right? In which case 2 KPA is not 2 kilonewtons per meter, right? Yeah. Okay. What about G? What's G? Yep. So it's 1 kPa times 1 meter. Is that it? So we've accounted for the superimposed dead load of 1 kPa due, yeah, whatever. So superimposed dead load is due to partitions, right? What are we missing?
The weight of the slab.
Exactly. The dead load due to the soft weight, right? So how do we get that?
Find the area and try to find the density.
Yeah, very good. It's actually, yeah, actually it's not density, it's the unit weight.
Actually, it says density right there, so I think it's density.
They will use that word interchangeably, but it's unit weight.
Actually,
So they said 25, okay.
actually it's 25.
Thanks, Caden. All right, times by use of area, right? So you tell me what the area is. Fuck.
Oh, it's trying to find itself.
Sorry, say that again.
1,000 times. Are you stupid?
One kPa is from the question said that.
So if I put that in my calculator, does that look right? So 1 plus, you know, 25,000 or whatever, 2 million.
The self weight is like 1
So what's?
All the way from 1 times 0.1. Sorry,
Yep.
my bad.
No, it's alright, it's alright. No, like, it's not your bad. I'm trying to like point these out so you don't make the mistake in the finals.
Just the depth of the drill, because the width is
So that's 5.75 kilonewtons per meter, right? So now we have our unfactored loads, right? Yeah. Okay, what's the next step? Well, I already said it here. It's load factors, right? Spoiler alert. So this one's this one. And this one is 2. So which one is going to govern?
Sorry, can you repeat that?
Which load combo is going to govern? Yeah. 9.9, right? Yeah. So this is going to be the number we're going to roll with. Okay. Next, we're going to find M star, right? We're dealing with continuous beam, so we're going to use the simplified method, right? Which is from the standards, it's this graph. And yeah, so we have, I've grabbed it from the screenshot, which is like greater than 2 spans, because it says it's for 4 spans, right? Okay, so we're designing this end span, right? Where do you reckon the max moment will be? In the middle here? You sure? So that's right. So that factor is going to be this, right? It's going to be positive bending, right? This point here is going to be a negative bending, right?
Yes, man.
Which number is going to be bigger?
Top one.
Yeah, the middle, right? But what about this one?
Bottom one.
Yeah. So there's actually a bigger hogging moment at this first column than the middle as a sagging moment, right?
Wow.
So we're actually designing for this negative magnitude of moment or whatever, right? But that's still what we're going to design for, right?
Wow.
Oh, sorry, kilonewton meters, right? So this is the greatest magnitude, so this is going to govern our section sizing. Okay. So, oh, by the way, I should mention, because this is a hogging moment, right? So our tensile steel is going to look like this in the primary direction. You know, we want our tensile steel on the bottom, and then here we want our tensile steel on the top, right? However, I'm going to assume there's the same amount of tensile steel in the middle as there is on the side. So I'm going to draw it as if the tensile steel is like on the bottom side, right? Even though the moment was governed from the hogging moment. Yeah.
Okay.
Okay, so the clear cover was 25 mil. What is our depth to cover? Like
165.
Where'd you get that number from?
Oh, 190 minus 25.
Okay, so that
175. Wait.
No, 160.
you're right, but it said the clear cover. What's the difference between the cover and the clear cover?
Both sides of it, yeah, it's an extra.
Yeah, so we have to add on the radius of the bars, right?
So it's an extra 25.
Well, we have to subtract. Basically, clear cover is like that, and then we have the radius of the bars.
So it's just
But we're not told what the radius of the bars are,
Yeah.
so we're gonna assume the N12s.
And we're assuming that as well.
Yep. So that whole thing's gonna be 6 mil, right?
Do we assume that for any question that we give? So that we can reduce the bars, it's not.
it's like
There's no rule for this. It's basically N12 because I don't know. I actually don't know. This is N12. N12 just seems like a good like bar size to use. You know what I mean? So just assume it's N12.
Trust me, bro.
Yeah, trust me, brother.
That's the source. Trust me.
Yeah. Well, think about it like this, right? A slab, a typical slab looks like this with 200 mil depth-ish, but a beam will look something more like this, right? This one might be like 600, right? So the beam might have, I don't know, N20, N16, N24, something more like that. Whereas a slab, I think N12 is like more reasonable. So it's based on like the vibes of like how deep this section is.
Based on that.
Yeah, I think, yeah. There's no rules for it though.
Yeah.
So just for a slab, I would just say N12 because this question says so. Yeah. So that's the depth, effective depth, which is the same as the depth to the tensile steel because only one layer, right? Yeah. Okay. So is anyone familiar with this, formula?
okay.
Okay, this is called the preliminary size formula. So basically, it's because we have too many unknowns. So we're gonna have this variable called j, sometimes called x, sometimes called open box, right? And it's equal to 0.95 for rectangular sections. And this is a rectangular section because it's a slab, right? So after we plug in all those numbers, right, 24.75 times 10 to the 6, right? I've converted that to Newton millimeters, right? Because we want this in millimeters. Right. We want this to be ductile. We were told this was 500. And then here we calculated that effective depth, right? So basically our steel has to be greater than 386, right? This is just a preliminary size range, right? Okay, but the reason why we need this preliminary size, right, is because in this number, we use this number to find the depth to the neutral axis. So we want like a ballpark number to find the depth to the neutral axis. So here's where we plug this in. I've calculated, everyone knows where these are from, right? On the right hand side. Okay. Okay. Oh, and sorry, this is from force equilibrium. I've just kind of skipped this step, but you can see on the left-hand side, it's we only have one tensile force, which is the steel, and we only have one compressive force, which is the concrete, right? So in the ultimate moment, it's just those two, right? So we can solve for dn by equating them. So dn is 8.5, right? So just have a think about that for a second, right? This is like kind of typical of a slab. So the total slab depth is 190, right? From the bottom, we have 25 plus 6, right? The depth to the neutral axis is here. It's only 8.5 millimeters down. So you reckon we need compressive rear? If the depth to the neutral axis is only 8 mil from the top, do you reckon we need compressive rear?
No.
Yeah, exactly. Because you only need compressive rear to shift the neutral axis up. But if you have compressive rear, it will actually do a negative thing because it needs to clear the cover checks, right? So actually shift the neutral axis down. Yeah, so it'll actually be tensile rear, right?
Why would we want the neutral axis to be as high?
Okay, so basically, the higher our neutral axis is, it means that our tensile steel will do more. It adds to the ductility. But this is already a really shallow neutral axis. You know what I mean? For slabs. And that tends to be the case because our concrete can take on so much because it's fucking 1,000 mil wide, which is quite wide, right?
It happens to be into that. Is that necessarily harder to calculate, or is it
Are you talking about flexure, shear? Yes. But we're not doing a T-beam at the moment, but I know what you mean. You mean for a T-beam, right?
Yeah.
It is harder because you need to calculate the strength of the compressive concrete is basically this area, right? But like this part is a function of dn, and these ones are set if you have if your neutral axis goes into the web, basically.
And like if we add like reinforcement and push it the offensive plus, can you do that?
Yeah, that's actually one reason. I think there's a workshop question on that.
Is it?
They add compressive Rio so that it stays in the flange. Yeah. It is a good idea, yeah.
So,
But it's not because, usually in real life, it's not because it's harder to calculate. There are ways to calculate it, it's just a little bit more inconvenient. But they add it because it's also safer. The higher the neutral axis is, the more ductile your section is.
so do you reckon in the exams we could have, like, we could need to add a compressor view as well? Because
It's subjective though. It's really subjective, so it's really hard to mark. So I want to say that would be kind of unlikely.
I think it would be safer to just stick to the tensile one because that's like the main one.
You should definitely do what the question says. If it says add this, then do it. But if it doesn't, then don't do it because it's not part of the steps. Yeah, they'll be really specific with these questions. But yeah, in real life, you'd have to use your like designer's like intuition or like engineering intuition and then figure out what's best. But for an exam, it's really hard to gauge because like there's so many, like there's a million different variations on that they could do. So it'd be really hard to assess. Yeah, very good. Yeah, okay, sorry, I'm moving really slow. This is slower than I thought I was gonna talk about this. I haven't even finished Flexural. Okay, so adjusted AST range, right? So what have we changed? Well, we have a DN value now, but we're going to pretend that the AST wasn't the same value that we calculated before. You know what I mean? We needed an AST value, like an initial AST value, to get a DN value. And using that DN value, we have a refined AST value, right? So that's what we're doing. Yeah. And we plug in all these numbers. I'm not going to rewrite them. They're basically the same as before, right? But we get a new refined area. But this is just a range. Like we haven't finalized our AST value yet, right? We need to calculate the minimum steel required. So for alpha B, it's 0.2 if it's a rectangular beam. So if you remember, there's like some really shit formulas for if it's a T-beam, like, and if it's in hogging or in sagging. but for a rectangle like a slab, it's really easy. You plug in all these values again. Sorry, I'm not going to do all these. This one's kind of new. Not really. It's this. BW. It says B web, but a web and a flange is like there's no difference because we're designing a rectangle, right? So this is just 1,000. Yeah. So that's the minimum. So obviously we have to check whether this is greater than the AST value later when we finalize our AST value, but we don't have a finalized value yet. We just have a range. Okay, so basically bar spacing. So I've got a question for you, right? If we're designing per meter run, so this is 1,000 mil, do we need to stick to a integer for the amount of bars? Like, so for example, 4 or 5. Why? Are you sure?
Yes.
You actually can, because we're designing per meter, so this can extend for many meters. So you can actually have 4.5 bars or 4 point whatever. Oh no. Sorry, I didn't hear you. But like, yeah. So keep this concept in mind. This is for a slab because we're designing per meter run, right? Okay. So what's important is the spacing, right? Because this value of spacing is actually more important than the number of bars per section. Because it's like, okay, how far are the bars placed apart and then what areas per bar, you know? So if we're doing, if we're choosing N12s, right, which we will, this value for a single N12 is 110. The AST that we've narrowed the range down to has to be at least this amount, right, of Rio. And so we're going to rearrange for S by multiplying 1,000 onto this side. And then S is going to be this. So, oh, by the way, how would you calculate the spacing of the steel? Right? Like, oh, sorry, how would you calculate, yeah, actually, how would you calculate the spacing of the steel in terms of the width of the slab? Ooh, I like the way you think, but it doesn't need to be an integer. It doesn't need to be +1 or anything like that.
And divided by the width.
Width divided by n, right?
Width divided by n.
Yeah, exactly. So width divided by n is the spacing essentially, right? That's what we're saying here. So, yeah, anyway. Basically, we're gonna, so because it has to be less than this number, we're gonna set it to a nice number, rounded to the nearest 10, right, down, because again, like, smaller spacing means it's stronger, right? So 290. So now we're going to finalize the steel area. And we can do that by subbing in all these values. So this is basically the steel area per meter run, or for how much we're designing our slab for. And this is going to be the final AST value we're going to run with for the primary direction. So you're going to have to do a quick check. So these are slightly different for slabs and for beams. So this is just the slab check, right? And then because 290 is less than 300, this is okay. Right, 300 is the most you can have for steel spacing for a slab. Okay, secondary design. So we have a minor degree of crack control. So this is the formula that's given. These numbers can change a little bit depending on this number specifically. Basically gets bigger if you have a moderate degree of crack control or a high degree, or I think it's called a strong degree of crack control, right? But then this number is just 1,000 and this is 190, right? So that's just, yeah. So this is based on the area of the concrete. So it gives us this number, right? Okay, but now we have to check, okay, let's just say we're going to use N12s again for the secondary erection, right? we have to find that spacing using that formula again. So all I've done is I've moved 1000 to the other side. Yeah. And then this spacing value gives us it gives us 330.8, right? This exceeds that limit I was talking about of 300, right? So we set it to 300. We set the spacing to 300. So that means that our area is going to increase or decrease based on this formula. Like, sorry, as in here was our initial value based on that formula. Because our spacing has to decrease, are we going to have more or less secondary steel? It's going to increase the amount of secondary steel we have, right, per meter run. So we're going to set it to 300, yeah? And so doing that gives us secondary steel area of 367, right? So here's the final value we're going to run with. But, yeah, okay, so just keep in mind, 367 is the secondary steel area, and then 379 is the primary steel area, right? There is a rule that we have to check. We can't allow the area of the steel. Sorry. We can have more secondary steel than primary steel, but only by a factor, right? So the area of primary steel has to be greater than 75% of the secondary steel. So it can only be, if we rearrange that, it can only be 33% more than the primary direction, right? That's the rule. And when we plug everything in, we see that it's okay, right? So now we've done flexural design. Okay, I only have 3 minutes. I think I'll have to record the rest on like a Discord or something. I don't think I can run through this reasonably. You know, yesterday I was talking about how ripping the paper is like transverse shear, whereas punching through the paper would be like the equivalent of punching shear, right? Yeah. Which again is not covered in this course. But anyway, so it's actually based on the shear force diagram, and we can use a simplified method, which is like, it's a very similar looking diagram. Oh, it's actually not a diagram, but I drew it like a diagram. It's only described in the code through like these values. Yep. But I think I don't know, it's just more elegant diagram, right? So again, these values only apply for continuous beams. Give me 1 second, I'm just pulling something up. Here it is, okay. So we basically have to find the greatest V star, and if all these span lengths are the same, which we can assume because they give us ln is equal to 5,000 for this end span, but you know, we're only designing for this end span. So basically at this point, at the first support, first interior support, this is the value we're going to run with. So so the value, it's like a multiplication factor, I guess, like 1.15 over 2, and we're going to multiply it by W star, which we found was 9.9, and ln was, it's 5 meters, 5 meters, but it was written as, okay, what am I trying to say? It was written as 5,000 mil, but yeah, we're going to write it as 5 meters, because if we get kilonewtons per meter and multiply by meters, we will get 28.4625 kilonewtons, right? Yep. So this will be the value that we're going to go with. All right. So with shear design, basically the value for kV, right? This is I forgot the name for it, but this is a formula that depends on whether you have enough steel, area of shear steel per spacing. If it's greater than this threshold number that you can calculate or not, right? But we're just going to assume that it does satisfy the minimum steel requirement, in which case the formula is simply 0.15. And we're going to use a simplified method as well, where we just take the angle as 36 degrees. This angle, sorry, it's theta V. This angle is like, it's like when you have, I guess I explained this more in depth. Wait, Karan, have you had a chance to watch my shear design yap or no?
I think I have.
Yeah. Okay, so it's basically the angle of the concrete. Basically, this is the angle of the concrete cracking for shear, right?
That's correct.
Yep, and there's this really long formula for it in the detailed method, but we use the simplified method where that angle is just 36 degrees. That's a simplification which is pretty justified if you don't have pre-stressed concrete.
Yep.
So I think in your finals, like every shear question, like is going to be done the simplified way in the work solutions.
Yep.
Because it takes a long time.
That's correct.
Yeah. All right. So the next thing is the internal lever arm, right? And you know the depth of the slab 190. Little d was 159, right? That's like basically the depth minus the cover. And we take the maximum of those two numbers as the internal lever arm, giving us 143.1. All right. So since we have kV is this, I'll talk about it in a second. dV is 143.1, and the concrete compressive strength was 32. All right. So BV is the shear width, right?
Yep.
Basically, it's different for a T-beam. So for a T-beam, BV is the minimum between the width of the flange and the width of the web, right?
Okay.
So I guess like this is unrelated to this question, but which one would govern here?
The flange, no?
So the flange would be the bigger one. Like this
Oh
one.
yeah, sorry. Web. My bad.
All good, all good. So, basically in a T-beam, you're gonna see shear cracking occur in the web first.
Yeah.
Because basically we're saying that the concrete, I guess like area, I want to say, yeah, the concrete area in shear is always the thinner one that takes on like the shear first, or the majority of the shear, right?
Yep.
So that's when we have like something like a T-beam. Sometimes you have pre-stressed concrete like I-beams or I-girders and bridges, like pre-stressed steel and stuff. That's not in this course, but it's always in the thinner part, right?
Yeah, that's correct. I think that's pretty intuitive as well.
Yeah. It's actually, you've done steels, right?
No, I haven't.
Oh, okay. So in steels, we have I-beams, right?
Yeah.
And this web takes on the majority of the shear. So the shear distribution looks like this. You know what I mean? So the web will actually take on the majority of the shear. And that's always the case because it's it's to do with how thin the B value is along the depth. In terms of its ability to take on shear. Anyway, my point is, sorry, I'm just taking a long time to get here. For a T-beam, right? This is usually about, I don't know, let's say like 400 mil, maybe 300, I don't know, something like that for a T-beam.
Yep.
But we're doing a slab, right? So what would the width be?
Wouldn't it just be 1,000?
Exactly, right? So 1,000 is a really big number in comparison to this, right?
Yeah, so it'd just be 1 meter.
Yeah, it'd be 1 meter, which for shear, like for transverse shear's sake, is like, that can take on a lot actually. So you're gonna see this number, right? That's actually quite huge for resistance, right? Because if you remember, the external shear force is only this much.
Yeah.
Whereas the UC is this, right? And even with this reduction factor, right? This is like, this passes this test with flying colors, right?
Yep.
So the point is, slabs are really good at taking on transverse shear because the width is always 1,000, right?
Yep.
Yeah. Anyway, so that's why they don't need fitments. It doesn't need like the shear steel. So it says here, concrete is able to resist shear forces without the stirrups easily.
Yep.
Does that make sense?
No, it does make sense.
Okay, cool. Right, we'll move on to serviceability then. This will be the last part of the slab design, but it will be like a revision in serviceability, because last week I basically ran over the theory behind serviceability, but I didn't really do a question. So I think it really helps to see all the numbers like plugged in. Do you know what I mean?
Yep.
Do you remember what the serviceability, the short-term serviceability load combo is?
I wasn't there for that particular yap, I can't lie.
No, all good. So basically, okay, for strength, right? We have these ones.
Oh, 135G and 1.2Q, yeah.
But we actually don't use those for serviceability.
Yep.
Because serviceability is about deflections. It's about everyday loading rather than worst case scenario loading.
Okay.
Serviceability is about making sure that over time the slab doesn't deform too much. It doesn't warp out of place, basically, right?
Okay.
So we actually take a reduced load factor. So again, for strength, right, these are exaggerated factors. This is like, 1 in 100 years kind of loading, like really, really rare. Oh, sorry, like this is like worst case scenario loading, right?
Yep.
So that's like increasing factors. For serviceability, we actually take a reduction factor, right? This is the short-term 5 factor, and this is 0.7.
Yeah, and then the long term is 0.4, is that correct?
That's right, yeah. So we'll calculate that one later, but that's good, basically. Yeah, that's correct. So we'll plug in all these numbers and we can actually have a reduced... This is basically a number that's going to be less than just if you added the dead and live loads together. You know what I mean?
Yep.
Yeah. So that number is 7.15 kilonewtons per meter. Okay, great. So here's the thing. Here's something I want to amend from my yap last week. Because I said that for an end span, right? So this is an end span that we're designing for.
Yep.
Okay, that's end. That's wait, one sec. That's end, and this is like a interior span, right?
Yep.
So for an end span, I said that we only analyze 2 cross sections, right? Here and here.
Yep.
Because in the middle, there's a lot of deflections, and on the continuous end, there's going to be, I shouldn't say deflections. I should say it's because of the M star. That's not a good way to put it. Yeah, anyway, so this formula for IEF average, right? It takes 50% of what the effective I is here and 50% of what the effective I is there, right? That's what's required of that formula. So we analyze those 2 cross sections, right?
Yep.
However, we actually still need the M star value here, despite only analyzing 2 cross sections. It's because in the formula for deflection, right? It'll look like a fraction, and then it'll say you multiply it by M mid plus 0.1 from ML star and MR star. Do you know what I mean? So we still need this value for L, even though we don't need it for our IEF calculation.
Yeah.
Hopefully that makes sense. It might make more sense as I...
As you do it, yeah.
Yeah, sorry. I'm talking about it quite theoretically, but it's really hard to imagine like while, you can't see the numbers yet. My point is you should take MR, M mid, and ML from the simplified methods for continuous beams from the code, right? So these values are as follows. Okay. So my comment over here was just from what I was talking about earlier. But yeah, these are the values that we found, right, for our bending moment diagram.
Yep.
So basically, like, if we had our bending moment diagram, it would look like on the left, we have negative 11.2. You know, in the middle we have 16.3. On the right we have, you know, negative 17.9, right?
Yep.
That's basically what our bending moment diagram looks like for the end span. Okay. I don't know why I wrote that out. Just leave that there. Okay. So basically for serviceability design, right, we need IG and we need M cracked, and we check M cracked against the maximum bending moment, right, from our bending moment diagram. And then if it cracks at all, sorry, if this value is greater than this value at all, we have to calculate I cracked because we're going to need it for the IEF formula. Right. So serviceability is basically a bunch of rabbit holes that you have to follow.
Is it like when you're trying to calculate I cracked, is that just to readjust the M cracked value?
It's not to readjust the M cracked value, it's to adjust the IEF value.
Okay.
Basically, think about it like this. M cracked is a threshold number, which is like the bending moment at which your beam will start to crack.
Okay.
So it's like you have a bucket, right? And M cracked is the size of your bucket.
Yep.
And M max is the maximum amount of water that can fill your bucket. And then if it's full, then you have to calculate I cracked.
Yep. Got it.
Yep. Okay. But regardless, we have to find IG, and IG is the uncracked moment of inertia, right? And from solid mechanics, we use the transform section method. So just a reminder, that method is the one which is like, if you remember like the composite, you know,
Yeah.
timber and steel beams from like solid mechanics, it's the same method basically.
Gotcha.
And so we take the modular ratio as the stronger material divided by the weaker material and transform it. Oh, actually, it's not necessarily like that, but for concrete, you can remember it like that. For reinforced concrete design, you can remember it like that, right?
Okay.
And then, so you should get a number around 7. In this case, we got an exact number. We got pretty much exactly 7.
Yep.
So I'm just gonna round it to 7 because I think the answer on the calculator is like 6.98 or some crap like that. So just gonna round it to 7 to be nicer for calculations, right?
Yep.
Okay. So basically, I've got a question for you, Karan. Is the neutral axis the same thing as the centroid?
Not always.
That's true. That's correct.
Yeah. Not all.
But in the uncracked stage, it is.
It is. Yeah. It is.
So that's the stage that we're looking at right now. So we're actually calculating the centroid in the y direction, right?
Yep.
Which will be the same as the depth to the neutral axis if we're going top down, right?
Yes, that's correct.
Okay, so let's do that. So this is the centroid formula. This might look familiar.
Yep.
Let's take the sum of the areas multiplied by the depths, right, to those areas, and divide it all by the sum of the areas, right? So,
Yep.
Oh, by the way, sorry, I've redrawn the transform section here.
Yep.
So probably don't look at this one. Probably look at this one here.
Yep.
So what are our areas, firstly, that you can identify in that drawing?
Should be like the concrete, so like 190 times 1000 be
Perfect. Okay.
Yeah.
What's the depth of that?
to the center of it would be like 190 divided by 2.
Perfect. Okay. And then next we have one more object here.
Yeah, it's a steel beam or whatever. We have the area given 375.
Mm-hmm.
Yeah.
Okay. Here's the thing. When you do the transform section method, basically we're transforming this steel into concrete, right?
Yep.
And the method that we do is, let me just move this to the side. We basically have to multiply it by some number as if it was all made out of concrete, right?
Yeah, that's correct.
So we're turning the steel into concrete.
Yep.
And what we have to do is we basically extend it out this way to the sides, right?
Yep.
Like, yeah. And we multiply it by n, right? So that's multiplying it by 7. Because of its stiffness, right? It's essentially 7 times
Stronger than concrete.
yeah, stiffer than concrete, I guess. Is the
sorry,
more
yeah, right.
yeah, is like the more slightly correct way of saying it, right? So yeah, that's what we have to do, right? However, right? Sorry, I'm gonna redraw that seal there.
Yep.
We actually have to plug the steel back in. Okay, so actually it's easy to imagine it the holes, right? So before these were steel filling in these holes, right?
Yep.
But with the transformed section method, we actually plug them in with concrete.
Yep.
This is the way you're gonna have to imagine it. And what we do
Yep.
is we call this n-1.
Yep.
So it's actually gonna be 6 because n was 7, right?
Yep.
So essentially we need to do 6 multiplied by that to get the area. This is like almost like the effective area after you've done the transformation, right?
Yep.
Does that make sense, hopefully? Maybe.
I think we've done it in full workshop, so yeah, it does make sense.
Okay. What's the depth to this?
What beam? So what's the beam? Is it N12 bars we're using?
Yes.
Okay.
But it shouldn't
Does that
matter
matter?
here.
Yeah, it should 59 then.
Yep, 159. Because this is already the depth to the middle, right?
Okay, sorry. Yeah, just
Yeah, no,
wanted to
that's
answer
right. Yeah, because before we were given the clear cover, so yeah, you did have to account for that. But since we've already accounted for that, the depth is to the middle of it, so it doesn't matter about the radius anymore.
Alright, perfect.
Yeah. And then some of the areas, basically, we take these parts that aren't to do with the depth, right, and we just add them together.
Yep.
And then we get 95.75 mil. Okay, cool. All right. Do you remember what the the moment of inertia formula is?
Well, that's like BD cubed on 12.
So, what shape is this for?
For a rectangle.
Yes. So, I mean, from this transform section, which part are we going to model as a rectangle?
The concrete, no?
So that'll be basically that's it for the concrete. That's what we have to do for the concrete, right?
Yeah.
But now we have to add on for the steel as well, right?
Yeah. Okay.
All right, let's continue. I was right in that I was wrong. So basically, okay. So we have our section, right? Like it looks like this, and we have DN, right? Okay. So firstly, if our steel looks like this, would you suspect DN to be in the middle?
No.
Would it be slightly shifted up or down of the exact middle, like DN2?
Yeah.
Yeah, so this is DN2, as in just to the middle of the rectangle, right? But DN, oh sorry, I probably won't go to the steel. It'll probably sit like here. Sorry. Let's do that again. DN will probably actually sit like this, right?
Yep.
Like it'll be weighted down from the middle if everything's uncracked, right? So we actually have to account for that using parallel axis theorem.
Yep.
Okay, so parallel axis theorem is A times basically the difference between these two lines, so between this line and to DN. That's the shift distance, right? We have to shift it from where we've created the rectangle, so we've created the rectangle like basically in the middle of this rectangle, and we have to shift it down a little bit, right?
Yep.
So we basically subtract these two. It doesn't matter which order we subtract these two in. Oh, sorry. Let's call this 96, just for the simplicity of the calcs, right? And we square it, right? So this is just a formula, A multiplied by the shift squared. Does that make sense?
Yep.
Hopefully that makes sense. Okay, so we can plug in the rest of the concrete rectangle like this. right? Okay, what else do we need to account for the IG, which is essentially the bending resistance?
The rods.
Yes, the rods. So, which part of the rod would we have to account for? So this was basically the area of the rectangle for the concrete, right? This was the shift that we've accounted for. For the steel, do we need the rectangle, the shift, or both?
The rectangle.
Are you sure?
Is it both?
Are you sure, guys?
Is it the shift?
Because sorry, this is like almost a trick question. It's a trick question because of how we do the transformed transformed section method, right? So instead of this actually having like a radius, when we transform it into this line basically doesn't have a depth.
Oh right, yeah.
Okay.
Yeah, we would have squashed it down
I had
into a straight line. So it has a position and an area, right? The area being these two, but it doesn't have a depth. So when we add on the rectangle like this, BD cubed on 12, that represents the cylinders that are stretched out, right? Oh, sorry, the circles that are stretched out. D is 0, right?
They don't count. Oh yeah, they do.
But you know what does count? The shift counts, right? The shift for those bars. So we have to account for this shift here from the bars to the neutral axis or the centroid, right? So if I said it was area times, the distance like of that shift squared, like what would we plug in for that? So what's the area firstly?
And minus 1375.
Very good. Yeah, so that was AST by the way. And then, this one's 7. Okay, what about that shift? How would we get that shift? So for example, the shift we had to do for the concrete to the neutral axis was D over 2 minus 96, right? So for the steel bars, what would that be?
195 minus DN. 159, sorry.
Yes, perfect. DN is 96. That's from that's what we calculated in the previous step.
Oh yep.
Yep, squared, right? Yeah, perfect. That's all we have to do. That gives us the right answer. Done. Right. So now we have IG. Right. Okay. Next, right? We have to calculate the cracking moment, and before we can calculate the cracking moment, we have to find the reinforcement ratios. So PW is the tensile reinforcement ratio, and PCW is the compressive reinforcement ratio, right? Okay. So AST we've calculated, right? 375. Depth was 159. BW is can someone tell me?
Oh, 1000.
Very good. So, what this is saying, right, is it's basically saying area of tensile steel divided by width of concrete times effective depth of steel, right? Yeah. What it's saying is, do we have enough tensile steel divided by this area, essentially, right?
Yep.
That's what that ratio is. And that's 0.00236, right? Which is actually kind of low, but that's fine. It just changes something a little bit later, right? And what about PCW? What do you guys think that is?
What does PCW stand for again?
It's the reinforcement ratio of the compressive steel.
Oh,
So these bottom two values will be the same, right?
yep.
What about the top value? What's that going to be?
190 times 1000. Just a guess.
So 190 times 1000 is the concrete
Yep.
area, right?
Yep.
But this is the area of the compressive steel.
Ah, okay.
So what's the area of the compressive steel?
0? No, wait.
0. Because
We don't have compressive steel. It
Yeah,
was a trick. We only got tensile steel, right?
yeah.
Yep.
Okay. That means this component is going to be 0, right?
Yep.
And then PW is that number we calculated. And ES is the elastic modulus of the steel. And this was actually given in the question. I'm not going to scroll up, but it's just one of those things that's written, right? It said 700, this, I
Yeah.
think it said.
Yeah.
Micro thing, whatever. 10 to the minus 6 basically, right? And that gives us this. MPa, right? So this value is actually the it's the shrinkage. It's due to a cement shrinkage, right? But basically, when you have a uncracked concrete section, right, tensile steel like that, or whatever. Actually, it doesn't matter if we have steel in there. Oh, it kind of does. Okay, I'll leave it in. Basically, let me draw this. Here's our stress distribution, right? Looks like that. Because remember how we said the neutral axis will probably be bottom weighted?
Yep.
This is for a beam, for example, right?
Yep.
Which side will it crack from?
Oh,
Are you sure?
Bottom
Why the bottom?
is in tension.
Very
And
good.
concrete's weaker in tension.
Perfect. So this is where the concrete's going to start to crack, right?
Yep.
So actually here, the value we say that, like, so when a concrete beam is in flexure, right? At the like in the uncracked section, that value which governs where it cracks is called FTC.F, right? That's that value that's like 0.6 FC, right? That's the flexural tensile strength, right?
Yep.
And so in order to get what the moment of cracking is, right, we have to do Z, right? And specifically Z from the bottom. So Z is, sorry, this is spoiler alert. Okay, well, just bear with me for a second, right? It's Z multiplied by this, right? That governs our cracking moment. However,
Yeah.
we have this extra component to account for when we're talking about the shrinkage due to like the tensile stresses when the cement dries, basically, right? So when the cement dries, what it's saying is sometimes there's tensile forces that pull apart the concrete a bit more than you'd expect, and then it has a bit of cracking sooner than you'd expect, right? That's what sigma CS is basically, right? Does that kind of make sense?
Yes.
So instead of this formula, we're actually going to use this formula. Oops. So this formula accounts for that, right? This formula is saying, okay, maybe the strength or like the bucket size or whatever isn't as big as we expect because of this noticeable difference due to the concrete shrinkage, right?
Yeah.
Okay, I've got a question for you. So Z, right, has this formula, if you remember it from solid mechanics. I'll just do that, right?
Yeah.
But if we look at this, right? That y, right?
Yep.
If we look at this, the neutral axis isn't exactly in the middle, right? It's not d over 2.
Yep.
So we call this y top.
And y bottom. Yep.
Yeah, exactly, and y bottom. So either from the top or the bottom.
Yeah.
So which value for y are we going to use in this formula for the
Bottom.
cracking moment? Exactly, the bottom, because the bottom is where the tensile stresses are induced from, right?
Yeah.
So we use y bottom, and y bottom is the total depth minus the depth to the neutral axis, because the depth to the neutral axis is always from the compression side, right? So this will always give you it from the tensile side. Do you know what I mean?
Yep.
Okay. Sorry, that was a really long way of explaining that, but hopefully that makes sense. So we got these numbers. This is 96. This is 190. This was 5.806 times 10 to the 8, right? This was 0.6 times that, and this was that, right?
Yep.
So the cracking moment is 16.4 kilonewton meters, right? Okay, so basically, let's go back to up here. Sorry, here, right? Let's look at our bending moment diagram. Let's focus on this part for a second, right? What is our maximum moment?
16.3? Oh, no, 17.9, sorry.
Yeah, perfect. So that's our max moment, right? And as long as your beam, right, as long as along anywhere in the beam, you have a moment that cracks the beam, right? Like, aka this number, 17.9. As long as this surpasses this value here, sorry, let's do that again. 16.4, right? This was 17.9.
Yep.
If you have anywhere along the beam that cracks it, then you have to calculate I cracked.
Okay.
Yeah. And using I cracked, we're going to calculate the effective moment of inertia for those 2 points along the beam. The 2 points I'm talking about are the middle and the continuous span. What's the word? The interior support side. Yeah. So over here, there's no more supports. We don't have to calculate the IEF of that part, right? Okay, cracked moment inertia, right? So here's our cracked section, yeah.
Yep.
Like what makes the second stage of concrete, or the cracked stage, what makes it unique? Like what's its key features?
Cracks, I don't know. Sorry. Yeah.
So basically we say that the concrete on the tensile side is useless, right? So we disregard its area.
Yep.
So if you remember before, our depth to neutral axis used to be about here, right?
Yep.
And then our concrete was like still alive to here, right?
Yep.
But as soon as it cracked, it jumped up a lot. And what happens is it kind of jumped up it jumped up, quite a bit because, how do I say this? Here's all the cracked concrete, right? It cracks and is useless up until the neutral axis. And we say that the only part of the concrete we care about is it's the alive concrete its depth is the depth of the neutral axis. Does that make sense?
Okay.
So the area of concrete we actually care about is depth of the neutral axis multiplied by 1000. That's that area, right?
Yeah.
The other thing about the cracked stage of concrete is that we've kind of... Okay, let me draw this out. So again, this is for a beam. I think it's easier to see in a beam than a slab, right? That's where the concrete used to be, right? That's the concrete area I was talking about, which is like dn.
Yep.
But with our transform section method, do you see how the steel, sorry, like the concrete's not really there anymore next to the steel?
Yeah, and the steel isn't supporting the concrete, vice versa.
Yeah. So when we do our transform section method, right, like that, we don't need to do this. Do you remember how for the uncracked stage we did this?
Yep.
We can just draw the line straight across here, right?
Yep.
So essentially we're not plugging those holes back up with concrete. Does that make sense? I guess.
Yeah, because the concrete doesn't exist anymore. Or it's becoming useless.
Yeah. So instead of doing n-1, we've just switched to n. Because the concrete's exposed now, right?
Yep.
Yeah, that's basically the reasoning. Okay, so let's calculate dn again. We can still use the same formula as before, right?
Yep.
That centroidal formula, right? Okay, so how do I say this? All right, so just like before, we're going to get the area of the concrete, right, and multiply it by the depth. So how are we going to do that? What's the area of the concrete?
1000 times 96. Was it that?
Okay. I like how you're thinking about dn, right?
Yeah.
So
because I'm
96
not sure exactly where it's cracked.
No, you're right. So 96 was the depth before when we had the uncracked section, right? But has the depth of the neutral axis moved?
Yeah, it probably has.
So it's actually an unknown now that we have to solve for.
Yeah, okay, yeah, I was correct in saying that.
Yeah, so we just do 1000 dn. What about, where is the middle of the concrete? That rectangle?
dn2. dn12, sorry.
Perfect, right? So that's actually our expression for the concrete area and its depth, right? Okay, what about the steel? You know, these bars down here. What's its area and what's its depth?
Did we just use what we plugged in last time? Except we just used 7 instead of 6.
Perfect, yeah. So we do NAST instead of n-1, right? And you're right, so we do 7. And the steel area hasn't changed because we calculated that in the first part, right? And the depth hasn't moved either, right?
Yeah, right.
So for the area part, we just do this, and this is the area, right? So do 1000 dn plus 7 times 375, right?
Yep.
So this is not like an easy, last time we did this and we got 96, right? It's not like that anymore because now we have to solve for dn. So there's dn on the left-hand side and there's dn on the right-hand side, you know what I mean?
Yep.
I'm just a bit confused with the DN.
Mhm.
So it cracks at DN when it does.
So,
And,
sorry, yeah. Please keep going.
and the DN has also moved up, so it cracks after the DN has been shifted.
Okay. Basically, right? Before it looked like this, right? Oh, it's not a good drawing. Probably like this. This is the best drawing. Right? Before it was uncracked, DN was 96, right?
Yep.
So what happens once it reaches the cracking moment, right? Is that the tensile concrete starts to give and it's brittle, right? It starts to give very quickly and then these cracks start rising, right?
Yeah.
And it reaches an equilibrium point, around here. And then all that's cracked.
Oh, okay, so it's like a separate point.
And then it stops cracking around here. This is the, oh sorry. Stops cracking like around here. So this is the crack stage of concrete now. The crack stage is like where the cracks stop propagating, and it only stops propagating because we have the steel to balance it out. You know what I mean? Because if we didn't have the steel, it propagates and just it's completely fucked. Like there's nothing else to it, you know, like it will become zero. Like, you know, that depth becomes zero. But because we have that steel to balance it out, now the crack stage is like what the equilibrium point is after our moments exceed M cracked, right?
Oh, okay.
But
Cool.
that equilibrium point it's gonna be found using this quadratic kind of equation. Because again, we have two things depending on the depth of the neutral axis now. The centroid formula and the actual depth of the concrete. Does that make sense?
Yep.
Yeah. That's why we have to solve a quadratic here.
Gotcha.
So we multiply both sides by this denominator, the fraction denominator. So that moves it across to the left, right? And then it ends up looking like this, right? So that's that. And this is this multiplied by this, right? And what have I done here? I've basically subtracted 500 from both sides, which results in that. And then I've subtracted both sides by NAST times 159, right? And now we have something that looks kind of like a quadratic equation where we've moved all our components to one side and the other side is equal to 0, right? But there's this little trick I like to do to make the quadratic equation less annoying to plug into your calculator, and that is dividing the entire, all the components, right? So in quadratic equation, we have A, B, C, right? This is A, you know, this is B, the negative as well. This is C, right? I like to divide it by A, right? Actually, I might just leave those there. So now this is 1, right? So A divided by A is 1. B divided by A is that. And C divided by A is this, right? Because we're allowed to do this because the right-hand side is 0. So we're keeping it mathematically the same, right? But this makes the quadratic equation super easy because every time you see, like, you know how we divided by 2A and stuff like that, and then, you know, this is the A in here as well. That just makes the quadratic equation a lot easier to type into your calculator. And we get the same answer, right? Do you see how the depth of the neutral axis has changed a lot? So before it was 96 in the uncracked stage?
Yep.
Yeah, anyway. So it shifted up a lot. Alright, so we've got another part that takes a while, right? The moment of the cracked moment of inertia, right? How do we calculate this? Like, what did we do last time for IG?
Hey, my mic keeps turning off. We just used the, what's it called? The inertia of the concrete. So we just used BD cubed on 12 again, but we used the depth that we just calculated now.
I'm gonna call this the shift, right?
Yep.
Okay, thing is, this is one way to do it, right?
Yeah.
Because you're right, you can do dn, like inside for the shift, right? You can do dn, let me think about it. It's like that. You can do dn on 2 minus dn, I guess, right? To shift it.
Can't you just do the BH cubed on 3?
Exactly. So this is one way to do it, but I would recommend doing this. Because this simplifies this, and you get the same number.
Alright.
Because this formula comes from, you're allowed to do it. So this is the moment of inertia for a rectangle, but one edge of the rectangle is the neutral axis. So that is exactly what the definition is for our cracked concrete, right?
Yep.
So it's just much cleaner if we do it this way, right?
Yeah.
So that's what we're gonna do. And that depth is gonna be dn, by the way.
Okay.
Right. So width 1000, dn was 26.29, right? Okay, what else do we have to do?
The parallel axis, do you need that?
The rebar, right? Did you say?
Oh, no. Oh, yeah.
So we don't have to do the parallel for this anymore, right?
Oh,
So
shoot.
this is just this for the concrete. We don't have to shift it anymore if we do the over 3 formula.
Yep.
Okay, what about what's the other thing we have to do? It's pretty much the same thing, but a little bit different to what we did for IG, right?
Yeah. Okay.
So IG, did we do BD cubed on?
No.
Yeah. So because the bar is no depth, right?
Yeah.
So what do we have to do to account for the moment of inertia for the steel?
Just the area with the
Oh,
shift
yeah.
or something like that.
Yeah, perfect. So what's the area?
7 times 375.
Very good.
And then we just take the depth we've already calculated.
Which depth?
1.9.
Yeah, you're right. The
Oh.
the steel doesn't shift, so that's D, right? But
Yep.
is that the shift?
No, that's not the shift.
What do we have to do to it? Because this is the
Ah.
shift, isn't it?
Yep.
So what do we have to change that number by?
It would just be like. Oh, it would be 96 minus the DN value we just got, 26.29? Or is that. am I-
Yes, but yeah, 159, right? 159.
Okay, yeah, overcooked. That's my bad.
No, we don't take we never use the old DN value anymore. This is only for the IG calculation and the cracked calculation.
Yep.
Yeah, this isn't for the I cracked calculation. DN has changed now.
Okay.
Yeah, that's all. All right, thank you. Okay, so it's that. Millimeters cubed, and that's our value for I cracked. Right?
Yeah.
Okay, so for IEF average, we need IEF mid and IEF right. Okay? So that's because of this, right? We need IEF mid and IEF right. Okay? That's just like the rule for an end span. So as we calculated before, the tensile rear ratio was 0.002, but that's actually less than 0.005, which is kind of like a threshold number. And since it's less than that threshold number, the maximum value that IEF can be at the midpoint or the right-hand point can only be 60% of the uncracked moment of inertia, right? So that value is this, right? Okay, so basically what I've done is for the mid, so we actually know all these numbers, yeah? We calculated that, it's the same number here, we calculated that. Those are all constants now, essentially, right?
Yep.
But this value is going to be unique for the middle value and the right value, yeah?
Okay.
Sorry, one thing to keep in mind. Okay. Sorry. Just be really careful of scientific notation here, right? So this was our value for IG, right? What do you notice about these two numbers, I cracked and IG? Do they look, fairly close together?
They do pretty similar to each other, but it's they have a factor of 10 in between.
Exactly. So one is actually around 58, and one's 5.3 when you multiply them out by 7, right?
Yep.
10 to the 7, I should say, right? So what I've done in this formula is, IG goes on the bottom actually, but do you see how I've written it like that? Because it's just a ratio between those two numbers. You don't have to write the times 10 to the 7, right?
Yeah.
Same thing with M cracked and MM, right? These, it doesn't matter if you have them in Newton millimeters or kilonewton meters, because if you convert them to Newton millimeters, you're just going to be dividing out 10 to the 6 anyway, right?
Yep.
So anyway, yeah, just keep that in mind. Yeah, the bottom is a unit list basically. This part is the part of units for this formula. Okay. But the value we get for the mid, the mid value of effective moment of inertia is 6.64, but that's greater than what is allowable because of our tensile steel ratio, right? So we have to set it to be at the cap, basically, right?
Okay.
So we've set the middle one as this now.
Yep.
And for the right-hand side, again, all these are constants, right? So all that's changed is this, right? But since it's squared, by the way, it doesn't matter if you put in the negative or the positive, right? This value is actually less than the threshold number. So we just keep it as is, right?
Yep.
And so for IEF average, for an end span, right? Like this. For an end span, we take 50% weighting and 50% weighting from the middle and the right in terms of what the IEF values are, right? That's the 0.5. And that's what IEF average is.
Okay.
Does that make sense?
Yep.
Yeah.
If it's an interior span, we take 50% weighting from the middle, and then we take 25% from either side. And that's what IEF average is for a interior span. Does that make sense?
Okay, can you do me a favor? Can you separate that diagram into two different sections?
Yeah.
So you just have it separate, like the 50%, 50%, and then the 25, the 25. Because like it looks a little bit messy if you just have it.
Yep. So like that.
Perfect, thank you. Actually, can you do one last thing? Can you just put like 1, 2 underneath both the diagrams in like blue pen?
Oh yeah. So this is end span. Do you want to see end span?
Yeah,
This one's interior.
Yeah, perfect, thank you. That's all I need.
Okay. So for short-term deflection, right? We actually want the L value. So the entire time, when we've done flexure, when we did shear, and now we're doing serviceability, right? We've just cared about LN, like the net span, which is between like the distance of the air basically between the columns, right?
Yeah.
But now we actually care about L, which is the real length between the supports, right? We take the supports as the middle of the column.
Yep.
So we had to calculate that for the deflection values, right? So the columns were 150 mil each, so we take it in the middle. And this is a value for L, right?
Yep.
Okay, so short-term deflection, we plug in L, that's what I'm talking about. EC, is 28,600 MPa, that's given in the question. This was the value we just took a million years calculating, right?
Yeah.
But as I was saying before, we used MM and MR to calculate IEF, right? But we also needed the value for ML because it's used for this formula. Does that make sense?
Yeah.
And keep the signage the right way around for values here. So if it's a hogging moment, it has to be negative, and if it's a sagging moment, it has to be positive.
Okay.
Yeah. So like for this particular formula, this is where whether you have positive or negative bending moment value really matters, right?
Yeah.
And here I've done 10 to the 10 to the power of 6 because these are in kilonewton meters at the moment, right? And to convert them to Newton millimeters, we have to multiply it by 10 to the 6. And that's because the rest of these are in millimeters. This is an MPa, which is essentially newtons per millimeter squared. And this is in millimeters cubed to the power of 4, right? So we want everything in like dimensionally uniform. Like it's basically this, right? This is a set of dimensions which work with each other, right? We're using this set, so we should keep everything to that, and you'll end up with the short-term deflection in millimeters. Okay, any questions?
No.
All right, I'm gonna go through the rest a bit quicker now. I've just written out the working, and I'm not gonna like draw over it. Okay, so we also work out the sustained deflection, right? And then we get the total deflection. So sustained deflection, all we've done is instead of calculating all that shit again, we're getting the long-term load factor. I think earlier, Karan, you said that the phi for the long-term load is 0.4, like the phi factor for the long-term load. That's correct. So we're just plugging in what W star L is for this, for the numerator in this fraction, right? Because we're dividing out our old W star S and we're multiplying it by the L1. So it's as if we did all those calculations again, but with W L star, right?
Yep.
And then we get that the sustained load was this rather than this, right? And then KCS is I forgot the name. The creep factor, I think. Creep shrinkage factor. And if we have zero compressive steel, which we don't have compressive steel in this section, right? This value is equal to 2. There's a extended formula for that in my notes from last week. But yeah. Oh, you know what? I might as well write it out. Is this right? And it can't be less than 0.8. So yeah, since we have 0 of this, it has to be 2, right? Okay. So now the total deflection is just the short-term deflection plus 2 multiplied by our sustained deflection, right? But we're not done.
Yep.
Basically, the question, here's where it gets a bit weird, right? The question said limit the deflection after the attachment of brittle partitions to basically LEF over 500, right? But attachment of brittle partitions, this is like a kind of weird thing which I've only seen in this question, but it's to do with incremental deflection. Brittle partitions is like the dead load. Do you know like how we've separated dead load into the dead load due to the self weight and then the dead load due to partitions?
Yep.
I don't know. Basically, it's kind of weird. It's basically we're removing the dead load. Wait, is that the way to say it? I don't know. It's kind of weird. This is what we have to do, right? So, you know, that value we calculated at was 4.52 mil from that really long calculation we did. Now we divide out the short-term load factor. We divide out the short-term serviceability load, and we multiply it by just the dead load. The dead load is the partitions and the self weight, right? And we get this value. And basically the incremental short-term deflection is equal to this, and the incremental short-term deflection is, it's basically in this load combination, right? We just care about this part, right? The 0.7 times Q, right? That's what
Yeah.
we're calculating essentially, right? And it's like as if we did all our calculations with for deflection with just 0.7 Q, and that gives us 0.89, right? don't ask me why.
Yeah. Okay.
This is what when it says like attachment of brittle partitions, it's talking about. I don't know, it's just talking about 0.7 Q and what the deflection is due to that. It's kind of cooked, right? So that's the 0.7 Q deflection, and we add on the sustained deflection, right? And that's the total incremental deflection, right? LEF is the minimum between the length that we calculated and the net length plus the depth of the slab. And